Thank you for attending this session. I am Shazeb Yusuf Khan presenting my research on vortex tubes. This work has been supervised by Dr. Usman Alauddin, Assistant Professor in the Mechanical Engineering Department and Director of DICE Energy and Water Innovation Center at NED University, Karachi, Pakistan. The focus of this work is to simulate Ranque-Hilsch vortex tube, optimizing its thermal performance. This presentation includes fundamentals of a Ranque-Hilsch vortex tube and identification of the research gap at first. Then computation methodology is discussed through grid convergence and validation through the experiment. Finally, CFD results are presented on which optimization of vortex tube is performed. Ranque-Hilsch vortex tube is a thermofluidic device that was invented by Ranque and optimized by Hilsch for practical use. This device has no moving parts and comprises of vortex generator at the inlet and two exits for cold and hot streams at opposite ends. High pressure gas is injected through nozzles tangential to the circumference at the inlet of the vortex generator, where the flow expansion occurs and a vortex is formed. This vertical flow proceeds to the hot orifice formed by the control valve and reverse to the cold orifice formed by an opening near inlet nozzles. Two streams are separated with different temperatures of high and low values compared to the temperature of inlet gas. The working mechanism has been suggested by numerous researchers. However, Maxwell's demon thought experiment and Fulton's concept of free and forced vortices are considered to be applicable. Maxwell's theory explains the thermodynamics and Fulton's theory explains the fluid dynamics inside the vortex tube. The energy separation is caused by recirculation flow inside the tube, where the stagnation point identifies the separation region. Stagnation point is the point where local velocity is zero due to the interaction of free and forced vortices. When inlet stream exhausts through nozzles and vortex is generated, the flow moves to hot exit with a decaying velocity, which is represented by a free vortex, while the reversal of swirling flow from the control valve increases the velocity, which is termed as forced vortex, forced by the control hot exit valve. There are commercially available vortex tube devices by Axiar Corporation that provides spot cooling in manufacturing and food companies. Also, air-cooled jackets are embedded with these vortex tubes where high temperature events occur. Furthermore, these devices are used for heating purposes as well as heating coolant and cold startup of diesel engine, where the hot stream is utilized for such applications. Thermoelectric generators are equipped with vortex tubes for high efficiency heat transfer and are under consideration for applications in tube wells in the petroleum industry. Also, solar TEG hybrid vehicles are being investigated by some researchers. According to flow pattern, there are two types of vortex tube, uniflow and counterflow. The uniflow vortex tube has both outlets for hot and cold stream at the same end, whereas the counterflow vortex tube has outlets at opposite ends. The efficiency of counterflow vortex tube is much higher than the uniflow type. There are three types of vortex tube invented so far according to geometric shape. Number 1, straight. Number 2, curved. And third one, conical vortex tube. The conical vortex tube has a divergent cone, which has already been optimized for small area application. However, the shorter chord length in curved vortex tube has more advantage for smaller area. Straight and conical vortex tubes have been investigated by various researchers, but curved vortex tubes have limited literature and there is a sufficient research gap to be filled. Thermal performance of a vortex tube can be determined by temperature differences and isentropic efficiencies. The cold stream temperature difference can be useful for spot cooling application, while hot stream temperature difference is for heating application. Furthermore, vortex tubes are used in power generation and the performance is judged by the total temperature difference between hot and the cold streams. Isentropic efficiency is the ratio of the actual enthalpy change and the isentropic enthalpy change. The isentropic efficiencies are classified similarly for cooling, heating and energy separation, which can be found by isentropic relations. The isentropic efficiency depends on temperature differences as well as total pressure and mass flow rates, where cold mass fraction is one of operating parameters of the vortex tube. Cold mass fraction is the ratio of mass flow rates of cold stream and of inlet stream. Operating condition of the vortex tube is determined by total pressure at inlet and outlets that follows three conservation laws of mass, momentum and energy. The cold exit pressure is lower than hot exit pressure and both pressure at outlets are obviously less than inlet pressure. Various researchers have performed experimental and computational studies on straight vortex tube, which include tube length to diameter ratio, cold orifice diameter, inlet nozzle size and number of nozzles, as well as angle and truncation of conical valve. Saidi and Volipur performed experimental investigations and found many optimum geometric parameters including length to diameter ratio, cold orifice diameter and number of inlet nozzles. They found that length to diameter ratio should be between 20 and 55.5, whereas cold orifice diameter should be half of the tube diameter. They used 3.5 mm nozzle diameter and suggested 3 nozzles are better for optimum performance, where they found maximum cold temperature difference. However, later on, Ranque et al. Performed experiments where he used smaller diameter nozzle and found 6 nozzles at inlet for better performance, providing maximum cold temperature difference. So there is no consensus. No agreement have been found for nozzle size and count, which should be carefully investigated. However, Ranque et al. Found maximum cold temperature difference by truncated length of hot conical valve, which is 6 mm length. Also, Aiden et al. Found optimum apex angle of conical valve, which is 50 degrees in vortex tube. Curved vortex tubes are only examined by Volipur, Bovend and Ranque et al., where Ranque performed both experimental and CFD analysis to find optimum curvature angle. They performed such studies on curvature angle of 5, 10, 40, 70, 90 and 120 degrees, whereas Bovend et al. Performed numerical analysis on curvature angles of 30, 60, 90, 110 and 150 degrees. Ranque found 10 degree curvature to provide the best performance, while higher angle leads to degradation. However, Volipur and Bovend suggested that curved vortex tubes have poor performance compared to straight vortex tube due to limited curvature angles in their experiments. The performance of curved vortex tube is yet to be investigated for curvature angles greater than 150 degrees. Where it is found that the performance is similar to straight vortex tube at 150 degree curvature angle, and thermal performance increases when curvature angle is increased from 90 to 150 degrees. Opposite effect occurs on increasing angle from 0 to 90 degrees. Therefore, the curved vortex tube has a potential for research. Similarly, optimization can be performed by finding optimum geometric parameters for curved vortex tubes. The computational model is set up according to Walipur and Niazi experiments, where straight vortex tube and curved vortex tube with curvature angle of 110 degrees were investigated. The working tube length is 400 mm and inner tube diameter of 19.05 mm, which is set with length to diameter ratio of approximately 21. Chord orifice is half of the tube diameter and nozzle diameter is taken as 4 mm, which is not mentioned by Walipur et al., but carried in computational studies of Bovent and Walipur. A small hot exit patch is generated by hot conical valve. The cold outlet is extruded by 1 mm near the inlet of the vortex tube. Also, two other curved vortex tubes are created with curvature angles of 180 and 270 degrees. The hot conical valve has an apex angle of 50 degrees, where its height is taken as 18.15 mm and diameter of 17 mm. Different truncation length of 3, 6, 8 and 12 mm are also used with conical valve for the computational model, where apex angle is kept constant. An unstructured tetrahedral mesh is created with randomly distributed discretized cells of the geometry at the junction of inlet and cold exit of the fluid domain. The hexahedrons are created across the swept area of both tubes. The quality of the mesh and the wall Y plus are two important parameters for generating the mesh, where the default Y plus requirements is set to more than 30 for the standard K epsilon turbulence model. The grid refinement is performed using 3 different grids based on Rickardson technique, and mesh quality is evaluated using the standard criteria. The number of elements range from 100,000 to 1 million. The Great Convergence Index GCI is calculated, which was proposed by Chelik et al. And originally based on Roche uncertainty computational technique. Pressure inlet and pressure outlet boundary conditions are used, whereas walls are considered to be adiabatic with no slip condition. Also, turbulent intensity and turbulent viscosity ratio are set to default. The inlet pressure is set to total gauge pressure of 2 bar, whereas cold pressure outlet is set to 1 atmosphere. The hot exit pressure is varied according to cold mass fraction, ranging from 0.1 to 0.85. The operating condition is set to 0 Pascal for absolute total pressure at outlets. Standard K epsilon model is found to be the best fit for the validation of experiments of vortex tube. However, RNG K epsilon model provides a good estimate of velocity. 3 equations of conservation laws are used where compressibility effect is considered. Steady state conditions are applied to mass, momentum and energy equations. Also, ideal gas equation is considered to determine change in density. 2 further equations of turbulent kinetic energy and turbulent dissipation rate are used with discretization of second order upwind scheme. Default under relaxation factors are set to solve the finite volume RANS equations, whereas RNG model is found to be difficult to converge and required decreased under relaxation factors. Convergence occurs after 1500 iterations, so the residuals are set to 10 exponent minus 6 for all equations, instead of energy equation whose residuals are set to 10 exponent minus 9. The Great Convergence Index is found to be reduced for fine grid where there is a little difference in cold temperature difference. Both straight and curved vortex tubes are tested for grid convergence, where maximum GCI is found to be 3%, whereas the average GCI for fine grit is 1.07%. Also, the asymptotic values are around 1, which shows that there is a few to no effect of further reducing cell size of the grit. The grit resolution is constant with a value of 1.45, that is the ratio of two consecutive grits. The extrapolated GCI error bands are formed with each GCI of cold temperature difference, representing in the plot as shown. The maximum GCI of 2% is found in straight vortex tube at cold mass fraction of 0.6. Also, curves of cold temperature difference for different grits are in agreement to convergence from medium to fine grits. Similarly, GCI is maximum in 110 degree curved vortex tube at cold mass fraction of 0.5, while same kind of convergence is observed from 3 different grits. The maximum GCI is 3% in the curved vortex tube. The experimental data from a published paper of Valipur and Niazi is used, in which straight vortex tube and curved vortex tube of curvature 110 degrees are presented. The cold temperature difference as well as hot temperature difference at different cold mass fraction are validated for both tubes. The standard K epsilon turbulence model provides the best validated results of CFD data in both straight and curved vortex tube. It is observed that the cold mass fraction of 0.3 provides the maximum cold temperature difference, whereas cold mass fraction of 0.85 gives the maximum hot temperature difference. Therefore, the optimum geometric parameters can be found at cold mass fraction of 0.3. Also, for power generation, delta THC can be formulated from the difference of hot and cold temperature values. The computational analysis is performed for 4 different truncations of conical valve with lengths of 3, 6, 8 and 12 mm. It is observed that the 8 mm truncated length provides the maximum temperature difference. There is around 21% cooling enhancement in curved vortex tube compared to non-truncated valve, while 26% improvement in power generation. The maximum power generation can be obtained at cold mass fraction of 0.7 in most cases. The reason for this improvement is due to the vortex formation at flat face of the truncated conical valve, which pushes the separation region a bit further towards the cold orifice region. The cooling efficiency, heating efficiency, and energy efficiency, energy separation efficiency are plotted as a function of cold mass fraction for different truncation lengths, and these plots shows that cooling efficiency is found to be best for truncated length of 3 mm followed by 8 mm, and it is maximum when cold mass fraction ranging 0.6 to 0.7. It is found that heating efficiency is best when truncated length is between 6 and 8 mm, and its maximum occur at a cold mass fraction of 0.5. The energy separation efficiency is also found to be the best for 8 mm, only slightly higher than at 6 mm, with their maximums occur at cold mass fraction of 0.5. The effect of curvature angle in the counterflow vortex tube is studied using CFD approach to obtain optimum temperature differences, including curvature angle of 0, 110, 180 and 270 degrees. It was found in numerical investigation earlier by Bowen et al. That the temperature at cold exit decreased further when angle is greater than 90 degrees. And cold temperature difference in 150 degree curved vortex tube was the same as straight vortex tube. The present simulation present some promising results in which temperature differences increase in the 180 degree and 270 degree curved vortex tubes as compared to straight vortex tube and 110 degrees curved vortex tube. The maximum cold temperature difference obtained is 5.3% higher than the straight vortex tube. The cooling and heating efficiencies are found to be slightly higher for curvature angle of 180 degree, while the vortex tube with 270 degree curvature has maximum power generation. For better visualization, total temperature contour plots and velocity streamlines superimposed on static temperature contours are formed at cold mass fraction of 0.3, where a slight difference can be noticed for high curvature angles. The separation region is reduced compared to straight vortex tube. However, there is constant number of vortices formed in multi-circulation region. The number of inlet nozzles is also an important parameter that should be carefully selected for designing the curved vortex tube. The result shows that maximum cold temperature difference is obtained where 3 inlet nozzles at cold mass fraction of 0.3. The use of 3 inlet nozzles is found to provide an improvement of approximately 10.3% in the value of cold temperature difference over curved vortex tube with 2 nozzles. Also, the maximum value of temperature separation is found to occur with 3 inlet nozzles with a diameter of 4 mm at cold mass fraction of 0.85. The temperature separation decreased when the number of nozzles is either increased or decreased. The isentropic efficiencies in cooling and heating follow the same trend, but the energy separation efficiency is better with 2 nozzles. It can be seen from the figure that as the number of nozzles decrease, the free vortex region at the periphery of the vortex tube widened, causing the hot temperature region to expand. The nozzle count affects the initial swirl. Higher the initial swirl, higher will be the energy separation, which would gradually deteriorate under the influence of the secondary circulation flow. The reason for the decline in the energy separation process is turbulent mixing. Though the multi-circulation region is still present, but the increase in the mass flow rate resulted in the expansion of the free vortex region. However, there is still consensus with nozzle size and count. Ranque et al. Suggested that there should be 6 nozzles for better performance, but they used smaller diameter of nozzles. The exit pressure values are also affected by nozzle size, which is represented by the inlet nozzle diameter. Different nozzle diameter of 1.5, 2, 2.5, 3 and 4 mm are selected to investigate the effect on the thermal performance of 110 curved vortex tube. The interaction plot of cold temperature difference, hot temperature difference and temperature separation depending on nozzle diameter and number of nozzles are plotted using the CFD results, where 3 nozzles and 2.5 mm nozzle diameter is found to be better configuration based on cold temperature difference, whereas 4 nozzles and 2.5 mm diameter of nozzle is better configuration based on hot temperature difference. Also, there is a slight difference when 6 number of nozzles are selected with 2 mm diameter, and it can be observed that for all the trends of temperature differences, 6 nozzles with 2 diameter is better configuration. The reason for this intermediate selection of nozzle size is due to turbulent mixing from greater nozzle diameter and rapid flow expansion from smaller diameter. The number of inlet nozzles of greater diameter increases the turbulence, which pushes the flow further, causing a reduction in thermal performance. Smaller diameter reduces area and mass flow rate of the inlet, which results in low pressure at the vortex core, which is due to flow expansion similar to a divergent nozzle. It is found that the pressure loss resulted in a reduction of energy separation when a small nozzle of 1.5 mm diameter is used, which compromises tangential velocity inside the tube diaphragm. Finally, the optimized curved vortex tube is suggested, in which nozzle diameter, number of nozzles, truncated length, and curvature angle is properly selected. The hot and cold stream isentropic efficiencies are found to be better for curved vortex tube than straight vortex tube. Also, the energy separation efficiency of the curved vortex tube is higher when a smaller nozzle size is selected, so that there is a high pressure drop in the tube diaphragm. The maximum cold temperature difference for the curved vortex tube with optimized geometric parameters is found to be 28.67% higher than the straight vortex tube. The maximum temperature separation for the curved vortex tube with optimized geometric parameters is found to be 70.22% higher than the straight vortex tube at a value of cold mass fraction of 0.85. Thank you for listening. If you have any question, you may ask.